kind of funny. I wrote my first computer program in 1963. And so in that sense, I'm really high tech. I've been writing them every day since. And in other senses, like, I hate smartphones, so I'm totally not high tech on smartphones. I consider them the greatest evil ever invented. Anyway, I have one. When you call me, there's a message that says, this phone is not monitored. It may be a month before I turn this on and get your message. So you want to get in touch with me, send me an email. Okay, anyway, so we'll get me out of the way while you're still asleep and see where we're going here today. Do you guys want these lights off to make this easier to see, or does it matter? Okay. Okay, so anyway, two things to do today. We're supposedly talking about light in this class, so we should talk about just what light is and is not, and then we'll have maybe like 10 or 12 view graphs of sort of talking about light itself, and then we'll get into radiometry, and we've been throwing these terms around about radiance and irradiance and so forth. So we'll actually define those, talk a little bit about how you actually measure these things, which you're going to do in the lab this afternoon, and then this basically sets up the theory part of radiometry. The next lecture by Ken is going to give you the experimentalist view of how things work. So between the two of us, maybe you'll figure it all out. Okay, so just kind of a brief history of light. Every culture, or well, maybe most cultures anyway, have some, idea about what light is. And, the ancient Egyptians thought it was a luminous fire from the eye of the sun god Ra, that sort of thing. Well, the first real thinking about it was in ancient Greece, this fellow Democritus, who gave us our name democracy. He decided purely on intellectual reasoning without any evidence that everything should be made out of particles, which he called atomos, which became our word atoms, and that included matter and light. Well, that's kind of where it sat. And then in the Greeks also had the idea, for example, that the way you see things is that these particles come out of your eye and they go over and they some way sample the world and report back. Now, I've never seen any explanation of why everybody's eyes quit sending out light when the sun went down, but they're theoreticians, they're not experimentalists. So anyway, the next real progress came in the 11th century. There's a fellow named, it's usually called Alhazen in English. He was basically an Arab Isaac Newton who doesn't get the credit he deserves. So he did a number of things. He did simple experiments that showed that light travels in straight lines. He showed that this Greek idea of eyes emitting something which went out and came back was just completely wrong. He figured out Snell's law, for example, but of course he didn't get credit for it because nobody was reading Arabic. Anyway, then finally in the 1630s, René Descartes decided that light was waves, and along about the same time, Newton, doing his experiments with prisms and so forth, decided that light was particles, which he called corpuscles. And Newton didn't have any way to observe things like diffraction by light. So it looked to him like light just went in a straight huygens and, it didn't diffract around corners and so forth. So he thought it had to be a particle. And then about the same time as Newton, Huygens and Fresnel were doing a bunch of math and physics, and they decided light had to be a wave. And then what supposedly settled it, 1803, Young did an experiment that we'll talk about in a minute, which seemed to conclusively show that light was a wave. And then in the late 1800s, late 1860s, Maxwell came up with his theory of electric and magnetic fields governed by his famous equations, and then he was able to show that the propagating electric and magnetic fields traveled at exactly the same speed as light. So that really settled it, that light was a propagating field of electric and magnetic waves. Well, that seemed to settle. At the end of the 1800s, there's no doubt about it, Newton's wrong, light's a wave. Then in 1905, well, actually in here, Planck came up with his formula to explain the black body radiation curve, which was a big, mystery as to how that worked. But in order to do that, he had to assume that light was emitted and absorbed in discrete pieces, which he called quanta. And he wasn't sure that that was really happening. It was maybe just a mathematical trick to get the math to work out. But then shortly thereafter, in 1905, Einstein was able to explain the photoelectric effect, which nobody had been able to explain as a wave phenomenon, but Einstein was able to explain it by assuming that light was in some kind of little quanta that got absorbed all at once by the material. So now the pendulum's kind of back in the other direction, and people like Einstein were not well accepted because it was so clear that light was a wave. And now Einstein's saying to explain the photoelectric effect, for which he got the Nobel Prize eventually, you have to assume it comes in discrete pieces. But that didn't go over too well. But anyway, then sort of in the early to mid like 1920s, 30s, that area, people began figuring out how atoms work, and the whole business of quantum mechanics came into being. And there, both light and matter both have wave and particle-like properties. And you will detect whichever one your experiment is designed to measure. So if you have like a diffraction grating, that's kind of designed to measure wave properties, so that's what you measure. If you've got something in, let's say, modern terms, like a CCD that's absorbing light, the absorption is set up, it's kind of basically set up to detect a particle property, so therefore that's what you detect. So that's where it stood for a while. There was another experiment in here I'll talk about in a second that sort of conclusively showed that light is particles. And then in 1926, a chemist invented the name photon, which has sort of been taken over as the name for light quanta, although the chemist didn't really intend that. And then finally, in the sort of 1940s and 50s era, they developed, they meaning people like Richard Feynman, this theory called quantum electrodynamics, which light is treated as photon particles, but they're very strange particles we'll talk about in a minute. And so then it's finally gotten back now that we're back to thinking of light as particles, and that kind of takes us back to where we started 2,000 years ago. So anyway, let's just talk about Young's experiment, which you probably all have done in a freshman physics class. But if not, what you have is an opaque screen here with a couple of slits in it, or a couple of holes. But let's just say it's coming out of the board in this direction, and these are slits this way. And then you shine coherent light onto it, so this laser's coherent light. But coherent means that it's all coming from the same direction, it all has the same wavelength. So when that light is incident onto the screen, it's blocked here, but it can propagate through the two holes, and then going all the way back to Huygens, each one of these serves as a little source of light waves propagating out, and where the waves propagating from each hole add together on a screen back here, you will either get bright bands, or where they cancel out, the peak of one wave and the trough of another add together and give you nothing, then you get dark bands. So when you do this experiment, you will get patterns of bright and dark bands on the screen back here. Well, the only way you can explain this is if light is propagating as a wave, just like water waves going through a hole in the wall, they propagate out the same way. So when Young did this experiment in 1803, people said, this really sews it up, light's a wave. And there were some other similar experiments that conclusively showed light was a wave. And that's why Newton fell out of favor. But then in 1923, this fellow Compton did an experiment where he shot gamma rays into a material. The gamma rays knocked off electrons, so this is just a material particle, say an electron here, the gamma rays would bounce off at one direction and the electron would be ejected from the atom in some other direction. And so he was able to measure the energy of the electrons and the wavelength of the scattered X-rays here. And this wavelength is different than the incident wavelength because part of the energy here went into kinetic energy of knocking the electron off. So in order to explain his data, he assumed that the incoming light was a particle with given energy and momentum. And of course the electron has, when it's kicked off here, it's going to have energy and momentum. So he simply used the laws of conservation of energy and conservation of momentum, although they're relativistic forms, and he came up with this nice simple little formula that related the angle of the scattered electron here to the wavelength of the scattered electron and then the mass of the electron kicked off here. Well, the only way he could explain this experiment was assuming light is a particle. So this plus Einstein plus whatever else was going on, the pendulum was now clearly on the side that light is some kind of particle. And he got the Nobel Prize in 27 for this work called Compton scattering. So here's the question now. Here's the Fresnel setup here. When we shine a plane wave on it of light, we get this interference pattern. But if light is really individual photons, just a lot of them together, what if we shine just one photon at a time onto this screen? What do you get on the screen back here? We shine one at a time, send in one photon, wait 3 days, send another one in, wait 3 more days. What do you see on the screen back here? Certainly, if you throw baseballs through holes in a wall, baseballs are not going to show an interference pattern, at least you wouldn't think so. Any speculations here? Unless you cheated, of course, and looked ahead at my next view graph, but that doesn't count.
Does it matter whether or not you try to determine the path like twice?
Yeah, okay, there's a lot goes into it, but here's the bottom line. This experiment was done in the early 1980s. You send the photons in one at a time, and then you collect, a photon will hit here, it'll hit here, wherever. You slowly then, one photon at a time, where they're collected over here on the screen, you'll build up the same interference pattern. Well, this was predicted by quantum theory. It was really hard to believe because in order to get interference, you have to have something passing through both holes simultaneously and then some way interfering with itself. But if photons are particles, you can't have a baseball go through 2 holes at once. But that's what you get. And here's there's a video on YouTube, and it's also in the library. There's a file called Single Photon Interference, MP4 file. It's about 10 or 12 minute video where they talk about how they did this experiment. And then you see these are screen grabs from that video. So here after 3 minutes, they sent in about, looks like 20 or so photons, so maybe one every 3 seconds or so. And it looks like you just get this random pattern. These are, there was a CCD array behind the 2-hole thing, so the collector back there is not a piece of paper you look at, it's a CCD array, and you're looking at literally the pixels in the CCD where the photon hit and was absorbed. And so it doesn't look like anything, a few minutes later, still not much to be seen. After half an hour, you begin seeing these interference patterns, and here's 6 hours later, thousands of photons, and you've built up exactly the same interference pattern, one photon at a time, as you got from something like this laser sending in a plane wave of light. So that was really the confirmation of the prediction of quantum mechanics that said this is what you should see, but it's really very mysterious and how that happens. So this physicist Richard Feynman, that probably most of you have heard of, he calls this experiment the fundamental mystery of all of quantum mechanics. How does a single particle go through both holes at once and interfere with itself? And the bottom line is, we don't know. That's just what light does. And it doesn't fit your everyday conceptions of how baseballs and water waves work, but that's irrelevant. Light is not baseballs and water waves. But the experiment really forces two things on us. First, we have to give up the idea that photons are some way they're little localized particles, and even small size or something. They don't have any well-defined size. They're certainly not little small particles like atoms are. And a localized particle could not pass through both slits at once and then interfere with itself. So this thing has to be some way sort of spread out in space. And we're forced to abandon the idea that photons take a particular path from one place to the next. In this case, they went through both holes in the screen at once and then somehow sort of recombine on the other side, and they get absorbed at one spot. So that's really weird. And when you do quantum electrodynamics calculations, so let's say this is a mirror, and you have a light source here, and you're looking at the reflection of the light in the mirror. Okay, so freshman physics, it says, the light comes from here, it reflects at this point and goes into here. And that's just the way light works. In quantum electrodynamics, in order to compute what you see here, you have to consider that light takes all possible paths from the source to the mirror to the eye. So it goes along this path, it goes on this path, it goes on this path, it goes on this path, and it goes on this path. And only when you compute all of these different paths and you add the results together, it looks like it's going in a straight line from here to here. But if you only compute this path, you don't get the right answer. So there's a book in the back here. I think I saw Emmanuel has it. Yeah, you know which one I'm talking about. It's called QED, The Strange Story of Light and Matter by Feynman, who got the Nobel Prize with two other people for developing this whole business. I don't think there's an equation in it, but he talks you through all of this kind of stuff. So you kind of begin to get an idea of how quantum electrodynamics works. And as far as we know, that's the way light actually behaves today. So the bottom line here is death to the mosquito. Here's a fascist anyway. All you can say is that a photon is created at some particular point. Like there's an atom in this filament of a light bulb, an electron changed energy levels, and it emitted a photon. And we know where that happened. And you can say that the light was absorbed by a particular atom